If a rocket engine detonates during flight, the mission is usually over. Period. For over 80 years, propulsion engineers have built their careers on this very principle. Combustion chamber instabilities nearly brought down the F1 engine of the Saturn V in the early 60s. Combustion oscillations have destroyed the European Vulcan engines. Thermoacoustic combustion instabilities are the nightmare topic of every thesis at the DLR in Lampolitshausen. If your combustion chamber pressure suddenly jumps by a factor of 20 and the whole thing becomes a pressure wave, then your engine is in 1,000 pieces on the test stand and you have to explain to your supervisor why. And yet today, from Huntsville to Houston to Pittsburgh and Lampolitshausen, some of the best engine engineers are working in the world in front of their screens working on rocket engines that keep exploding, and it's completely intentional. With a detonation frequency in the kilohertz range. Several thousand shockwaves per second, cleanly circulating in an annular combustion chamber with a diameter of just 68 millimeters. And it works. The technology that the rocket industry wanted to avoid at all costs for 80 years is now well on its way to becoming the most efficient propulsion system of the next decade. And it's coming faster than most people think. In April 2026, just a few weeks before this recording, a single prototype exploded continuously for 300 seconds without taking any damage. A few months ago, the DLR became the first institute in Europe to operate such a detonation combustion chamber with real liquid oxygen and hydrogen. And in May 2025, for the first time in the United States, a rotating detonation engine actually flew. Today we're talking about what scientists have considered the supreme discipline of chemical space propulsion since 1959, and what, until a few years ago, no country was able to fully control. We'll dive into the technical details. We compare what the Americans can do, what the Germans can do, what the Japanese have done, and what the Chinese claim. And in the end, I ask the question that really matters, not whether this technology works, but who will fly with it. My name is Serwin, and this is Mars Chronicles. The story doesn't begin in Lampolitshausen and not in Cleveland. It begins in Akademogorsk at the Siberian Institute of Hydrodynamics in 1959. A Soviet fluid physicist named Bogdan Wojciechowski observes something that should actually be impossible. He manages to get a detonation wave to continuously circulate in a ring-shaped chamber. Not just ignite and dissipate like in a pulse detonation engine, but actually circulate continuously. A quasi-stationary shock that approaches itself, igniting the fresh mixture at the next moment of its own circulation. The mathematics behind it is fascinating, but the practice is hell. Wojciechowski publishes his observations, and for the next 60 years, research groups in Russia, the USA, Japan, Poland, and Germany try to build a working engine based on these observations. They fail. Not just a little, but completely. The detonation dies out. The wave breaks up into deflagration, or the combustion chamber melts. On top of that, the sensors are too slow to understand what's actually happening. High-speed cameras from the 60s could maybe manage 1,000 frames per second. But a modern RDE wave travels around the combustion chamber at several kilometers per second and reaches frequencies in the kilohertz range. In extreme cases, up to 100 kilohertz. You need 100,000 images per second just to see what you've actually burned there. It's only in the last 10 years that the game has changed. 3 things have happened. 1. Additive manufacturing, that is, 3D printing in copper alloys and Inconel, which makes it possible to produce such combustion chambers in the first place. 2. New high-frequency pressure sensors that resolve up to 4 mHz. That means a pressure reading every 250 nanoseconds. 3. High-speed cameras that no longer blur at 180,000 frames per second. And suddenly, a phenomenon that could only be inferred indirectly for 60 years can actually be observed, measured, and controlled. Before we take a look at the players, we need to clarify one thing. Why go through all this trouble in the first place? What is so appealing about an engine that is constantly exploding? The answer lies in thermodynamics. A normal rocket engine, meaning everything you've ever seen in a Falcon 9, an Ariane 6, or a Saturn V, operates with deflagration. That's a controlled combustion in the subsonic range at more or less constant pressure in the combustion chamber. The propellants are injected, mixed, ignited, and they react. And the pressure with which everything shoots out of the nozzle at the back is essentially the pressure with which the turbopumps push the stuff in at the front. In fact, you even lose a bit of pressure along the way. That's physically correct, but it's not the maximum. A detonation is something different, namely a supersonic shockwave-driven combustion. The flame front moves faster than the speed of sound in the unburned mixture. And that has a crucial consequence. While in deflagration the pressure remains constant or drops slightly, detonation actively builds up pressure. You gain pressure through combustion. In English, that's called pressure gain combustion. And that's exactly the promise. A rotating detonation engine, or RDE for short, or in the rocket context RDRE, practically captures this pressure gain. The combustion chamber is an annular gap. Two concentric cylinders with a few millimeters of space in between. On one side, the propellants, typically hydrogen and oxygen or methane and oxygen, are continuously injected. You ignite it once externally with a so-called pre-detonator. And if everything goes right, a detonation wave starts and circles around in the annular gap, several thousand times per second. Every time it passes a spot, fresh fuel mixture has accumulated there, which is ignited by the passing shockwave, feeding and sustaining the wave. Hot, highly compressed gas comes out at the back and is expelled through a nozzle to produce thrust. Sounds crazy? It is. But the theoretical increase in efficiency is tempting. A much-cited study, led by John Benowitz at the Air Force Research Laboratory and published in Scientific Reports in 2023, estimates the realistic gain to be on the order of 10 more thrust with the same fuel consumption. In addition, there are smaller combustion chambers, lower required injection pressures, less susceptibility to classic combustion chamber instabilities, and a significantly smaller construction volume. In a world where every kilogram in the tank and every cubic centimeter of combustion chamber costs money, that's tempting. And if you now combine that with a ramjet, which is an air-breathing jet engine for hypersonic flight speeds, then suddenly you not only have a better rocket engine, but also the theoretical key to a passenger jet that accelerates from a normal runway to Mach 6. A small company from Houston, Texas is working on building exactly that. We'll get to that in a moment, but the first to show that these detonation rings actually work in reality weren't NASA, but the Japanese. On July 27, 2021 at around 5:30 a.m. local time, an SS-5 2031 sounding rocket was launched from the Uchinura Space Center on Kyushu Island. A configuration with classic solid fuel in the first stage. But in the upper section, there's something new. A detonation engine system built by a research group from Nagoya University, together with Keio Yakusa and the Muroran Institute of Technology, led by detonation physicist Hiroka Seihara. After the separation of the first stage, the crew ignites the rotating detonation engine in actual vacuum. Methane and oxygen. Gaseous. 6 seconds of operation. About 500 newtons of thrust. Pressure data, temperature data, and even video recordings are sent to Earth via telemetry and recovered from the Pacific using a small return capsule called RATS. It's the world's first detonation engine ever to run outside the atmosphere. 500 newtons isn't much. A Vacuum 9 has a total of 15,000 and many times more thrust than the Japanese experiment. But that wasn't the point. The point was to show that the physical principle works in space. That's very typical for Japanese spaceflight. Quietly, thoroughly, without a PR machine. but technically they're right at the forefront. The Americans took longer, but then they came with force. If you've stayed with us this far, you now know more about rotating detonation than 95% of all German-speaking spaceflight commentators. And it's about to get really wild. Hit hype if you have it. Otherwise, a like, subscription, or comment also helps the channel a lot. Let's continue. The center of NASA activity is the Marshall Space Flight Center in Huntsville, Alabama. At the center sits a combustion devices engineer named Thomas Teasley, who leads the RDR-RDRE test program, funded through the game-changing development program of the Space Technology Mission Directorate. Two tests define the current state of the art in the US to this day. The first was in the summer of 2022. A 3D printed rotating detonation combustion chamber made from a copper alloy developed by NASA itself, called GR-COP42. One manufactured using the powder bed fusion process in cooperation with InSpace LLC and Purdue University in Indiana. The thing produced over 4,000 pounds of thrust for almost a minute at a chamber pressure of 622 psi. According to Marshall, that's the highest documented chamber pressure for such a configuration. An initial hardware demonstrator result that showed additive manufacturing really is the key. GR-COP42 is a high-performance copper alloy with excellent thermal conductivity, which through additive manufacturing allows for the geometric complexity required by such a combustion chamber. The second test was the shocker. On September 27, 2023, Marshall fired the same engine type for 250 seconds. Over 4 minutes straight? With over 2,600 kilograms of thrust, that's a burn time profile that roughly matches a typical lunar landing braking maneuver, or a Mars transfer burn. In other words, NASA has demonstrated that this technology is no longer just a phenomenon lasting seconds in the lab, but is now operating at scales where real missions can be conducted. Meanwhile, the Marshall program is planning the next stage, a technology demonstration mission with a combustion chamber assembly in the 10,000-pound class. So that's a bit over 4,500 kilograms of thrust, coupled with a real methane-oxygen turbopump with a gas generator. That's no longer basic research. That's preparation for a flight-capable propulsion system. I want to pause here for a moment. This video is possible thanks to a company whose products have been on my desk for years. BenQ has been making monitors and eye care hardware for over 2 decades, and I work here in Vienna with 2 BenQ screens. But what I didn't have until recently was their latest monitor light bar, the Screen Bar Halo 2. And honestly, I don't understand how I managed without it for so long. A monitor light bar is exactly what the name suggests. A slim lamp that clips onto the top of your monitor and precisely illuminates the desk area, where your keyboard, your notepad, and your hands are. Not a classic desk lamp that either shines into your eyes or reflects on the screen. The Halo 2 uses a patented 3rd-generation asymmetrical optic with an 18-degree shielding angle, and directs almost 95% of the light precisely downward onto the work surface. No glare on the display, no eye fatigue, and the desk stays clear because the lamp sits on top of the monitor. The truly new feature of the Halo 2 is the rear lighting. A 3-zone backlight casts light upwards, downwards, and sideways onto the wall behind the monitor, which dramatically reduces the contrast between the screen and the surroundings. During hours-long writing sessions, and I've had quite a few of those just for this script, it makes a physically noticeable difference. The whole thing is operated using a wireless rotary controller with a digital display. With it, you can continuously adjust the brightness and the color temperature between 2700 and 6500 Kelvin. Warm light in the evening for writing scripts, cool daylight white for video calls and research sessions during the day. The Halo 2 also has an ambient sensor and ultrasonic precision detection. That means it turns on automatically as soon as I sit down at the desk and turns off again when I get up. The patented clamp fits practically any desk, between 4 and 6 centimeters thick, especially on curved panels, and there's a webcam adapter if your setup needs it. The Halo 2 was designed together with the design studio Minimal from Chicago and won both the IF Design Award and the Red Dot Design Award in 2025. You can really see that in the device. If you spend long hours at your desk, whether it's coding, research, writing, or editing, this is one of the few purchases I can truly recommend without reservation. With my code, Mars10, you get 10% off the Screenbar Halo 2 and free shipping as well, valid on the German BenQ website. Thank you BenQ for supporting Mars Chronicles. And now back to the detonation. While NASA in Huntsville has defined the standard procedure for institutional RDRE research, another class of actors has emerged in parallel. Private sector risk-taking with clear commercial visions. You need to know two of them because they have reshaped the field in the last 18 months. Venus Aerospace from Houston and Astrobotic from Pittsburgh. Venus Aerospace is a startup from 2020 founded by Sassy and Andrew Duggleby, a CEO-CTO couple with backgrounds in aerospace and fluid mechanics. Their funding comes from Airbus Ventures, Prime Movers Lab, America's Frontier Fund, and Trousdale Ventures, plus research partnerships with NASA and the US Air Force. Their vision is a Mach 4 passenger jet called Stargazer M4, which takes off from regular airports and connects Los Angeles to Tokyo in under 2 hours. That's ambitious in a way that would have been ridiculed as a pipe dream in the 90s. On May 14, 2025, they delivered something that no one would have expected just 12 months earlier. Venus Aerospace launched a small rocket with a rotating detonation engine on board from Spaceport America in New Mexico in the desert south of White Sands. 3 to 5 seconds of vertical ascent, 1,340 meters in altitude, a maximum acceleration of 4 G. And crucially, the engine was recovered almost undamaged after the flight. It was the first flight test of an RDR-RDRE in the United States, and according to the company, probably the first such flight ever worldwide, if you exclude the Japanese configuration as a low-thrust research facility. This means the detonation engine has finally moved out of the laboratory. Andrew Duggleby, the CTO, said a sentence after the test that will keep the industry busy for a while. Essentially, the rotating detonation engine has been a theoretically attractive thrust gain for decades. And Venus has overcome the final critical hurdles to finally realize this theoretical gain in hardware. Whether that's completely true will have to be shown by scaling, but as a vehicle demonstration, it's a milestone. Venus itself is aiming to combine it with its in-house air-breathing detonation Ramjet VDR-2, with the goal of a Mach 6 vehicle without an external booster stage. It's still a long way to go until then. But May 2025 was the proof that the core is real. You need to know the second private company, because just a few weeks before this recording, it broke a world record. On April 23, 2026, Astrobotic Technology from Pittsburgh announced the completion of a test campaign at the NASA Marshall Space Flight Center. The engine is called Chakra, named after the disc-shaped throwing weapon from Indian mythology, which is a fitting name considering the ring geometry of the combustion chamber. Astrobotic is best known for the Peregrine mission. In January 2024, the company became the first US private firm to launch a lunar lander, but the mission failed due to a valve defect in the propulsion system. Before Peregrine could even reach the moon. A painful lesson, but it didn't knock Astrobotic out of the game. Instead, they took the outcome as an opportunity to ramp up propulsion development internally. Chakra is part of this answer. What Chakra delivered in April 2026 is of a completely different magnitude than anything else so far. 2 prototypes have accumulated over 470 seconds of burn time in 8 hot fire tests. That includes a single uninterrupted run of 300 seconds. According to all relevant observers, including NASA, this is the longest continuous hot fire run of a rotating detonation rocket engine in history. Each prototype produced more than 1.8 tons of thrust, and both engines reached what's called thermal steady-state conditions. That means the engine ran long enough for the temperature distribution in the combustion chamber wall to stabilize and stop increasing. That's the thermal equivalent of true continuous performance. After the test, both prototypes were inspected without any visible damage. Brian Avalos, principal investigator of the Chakra program at Avalos Astrobotic, summarized the result in a statement that I would like to quote because it sounds honest. Essentially, with any cutting-edge technology like an RDRE, there is always the concern that unknown factors will emerge in the transition from design to actual testing, which could throw everything off. However, the engine actually performed even better than expected. And the 300-second run was the icing on the cake. That's a refreshingly calm way of saying that something worked that normally doesn't work. Astrobotic wants to integrate Chakra into several commercial platforms. On one hand, into future visions of the Griffin lunar lander, which is larger compared to Peregrine and is actually intended for cargo missions at the lunar South Pole. On the other hand, into a series of reusable suborbital launch vehicles based on the designs that Astrobotic acquired in 2022 from the bankrupt Maston Space Systems, namely Zodiac and Sogdor. Please write in the comments how to pronounce that correctly. But also into an orbital transfer vehicle for operations in cislunar space, that is, between Earth's orbit and the Moon's orbit. Chakram was funded through NASA's Small Business Innovation Research contracts and a Space Act agreement with Marshall. According to Astrobotic, the next development cycle will focus on regenerative cooling, meaning engine cooling using the propellant itself, on throttling, that is, controlled thrust regulation, and on mass reduction. The classics, right? Those are the three things missing to actually fly Chakram on a lunar mission. What you shouldn't overlook here is the underlying manufacturing technology. Astrobotic talks about tunable porosity metal additive manufacturing, ACID. An additively manufactured combustion chamber structure with specifically adjusted porosity in certain wall areas, optimizing heat management and detonation stability at the same time. That's the same phenomenon that played the main role in our LeapLeap 71 video a few weeks ago. Computational engineering and 3D printing are merging into the actual propulsion discipline of the next generation, and combustion chambers are no longer drawn by designers, but designed by algorithms and manufactured by printers. So, that's enough about the American side. If you just read the headlines, you might get the impression that the US is developing RDE technology on its own, and Germany is at best watching from the sidelines. That would be wrong. In fact, the German Aerospace Center at the Landbolzhausen site has been making some of the most significant European contributions to rotational detonation research for over a decade. And in March 2026, something happened there that few people in the United States took notice of. Landbolzhausen is a term that means little to outsiders, but for engine engineers, it is almost mythical. Every European rocket engine development process of the last decades has at some point gone through Landbolzhausen, says Jan Deacon, the head of the local DLR Institute for Space Propulsion. Vulcain, Vinci, Aestus, and Prometheus. And in the future, rotational detonation. The test stands M3.1 and Gesetzes. They are smaller, highly instrumented research facilities where detonation research is conducted. About 100 hot runs have been carried out there in recent years with an RDE configuration, mainly with hydrogen and oxygen, as was the case in the Northeast story. Gaseous methane and oxygen. The mass flows vary between 15 and about 250 grams per second. So these are deliberately small-scale research engines whose purpose is not to fly a rocket, but to understand the phenomenon physically. The combustion chamber in Landbolzhausen is a capacitively cooled ring construction made of a copper alloy. The outer diameter is 68 millimeters. Capacitively cooled means it has no active cooling channels, but instead acts purely as a heat reservoir. This works very well, but it has the disadvantage that the test times are limited to about 1.5 seconds before the wall gets too hot. In this short time, the detonation wave circles the combustion chamber several thousand times, and the DLR measures this with pressure sensors that resolve up to 4 MHz, combined with high-speed cameras at 180,000 frames per second. In November 2025, the Lampoldshausen team published a paper in the CES Space Journal about a functional hydrogen-oxygen pre-detonator. This is the ignition prechamber, which is flanged radially to the main combustion chamber and where the initial detonation wave is generated before it passes radially into the actual annular space. That sounds like a detail, but it's actually the core problem of the entire RDE technology. Without reliable, reproducible ignition, everything else is just theory. DLR Lampoldshausen now has one of the most difficult subsystems in the entire field built and working. And then on March 19, 2026, about 2 months ago, DLR delivered something that is considered a small sensation in European engine research. For the first time in Europe, a rotating detonation engine was operated with real liquid oxygen. So no longer with gaseous oxidizer, but with cryogenically liquefied oxygen, just like it is used in every real rocket engine. The oxygen was gradually cooled down to about minus 183 degrees Celsius, and the detonation waves stabilized. The DLR wrote in its Instagram post from the 19th. On March 19th, the DLR literally wrote that under these, quote, extremely realistic conditions, rotating detonation waves are generated that release energy particularly efficiently. The run lasted about 5 seconds. Before we put this into a political context, we need to briefly look at 2 other nations that complete the picture: China and the American defense budget. For me, China is still difficult to assess in the RDE sector, because most publications either come in the form of press releases that cannot be independently verified or appear in Chinese professional journals whose methodology sections are significantly less transparent than Western standards. With appropriate caution, there are 2 claims. First, a group from the National University of Defense Technology stated in May 2025 that they had run an RDE test stand trial lasting over 600 seconds, with an ethylene-oxygen fuel combination in a hypersonic wind tunnel environment. If that's true and could be independently verified, it would be significantly longer than the Western standard. Secondly, a group at the Beijing Power Machinery Institute published a concept in December 2023 that aims to couple a rotating detonation with a so-called oblique or slanted detonation in a 2-stage hypersonic engine, which would theoretically work until Mach 16. So far, it's just a paper, with no hardware validation as far as is publicly known. What can be stated is China is structurally very active in the RDE field, especially in areas close to the military, and treats the technology as a key technology for the next generation of hypersonic weapons, not as a civilian spaceflight option. In the United States, DARPA has launched the Gambit program together with RTX, a company that was formerly known as Raytheon. Gambit explicitly targets air-launched standoff supersonic weapons, meaning cruise missiles that are dropped from an aircraft and then independently fly to a target at supersonic speed. The Air Force Research Lab in Edwards and Wright-Patterson is simultaneously advancing the purely military line. If you ask where the money in the US comes from that has brought RDE technology up to the pace we're seeing in 2026, the answer is very clear. From the Pentagon. The civilian NASA application benefits from it, but it's not the driving force. That's a truth the European space community doesn't like to deal with. The DLR research in Lampoldshausen is scientifically excellent, but it's also scientifically designed, meaning it's aimed at gaining knowledge and not at an industrial scaling route. There is no Ariane Group contract in Germany that would include an RDE engine in the roadmap of a future European launch vehicle. Prometheus, the current European demonstrator engine, is a classic methane-oxygen combustion chamber with pump-fed propulsion. No detonation engine. If we're honest, Europe has excellent basic research, but no industrial policy vehicle that would translate this research into a flight hardware program. At this point, it's worth taking a step back and making an honest assessment. What can RDE, RDRE really do, and what can't it? The real efficiency increase compared to the current state of the art, according to the most reliable study so far, the already mentioned Beneviz work from Scientific Reports 2023, is on the order of up to 10%, more thrust with the same amount of fuel. That's significant, but it's not revolutionary. It's not the promise of tripling that you find in some tabloid articles. It's the kind of magnitude where an established engine engineer would say, that's worth it, if the effort is right. The really attractive aspects are more the secondary ones. Smaller combustion chambers, which in a lunar lander stage means more volume for fuel or more payload. Lower required injection pressures, which reduces the complexity of the turbopumps. Less susceptibility to the classic, acoustically driven combustion chamber instabilities that make every engine developer go grey. The more compact design plays a role, especially where volume costs more than mass, such as in cruise missiles, suborbital demonstrators, and potentially in upper stage engines that need to be integrated into launch vehicles. What RDR-RDRE is not is a finished propulsion system. The open problems are real and they are tough. Regenerative cooling is still in its infancy. Thrust control or throttling is not trivial with a detonation wave that has to stabilize itself. Gimbal control, meaning the mechanical swiveling of the engine for rocket attitude control, is basically simple with the low combustion chamber masses but untested in integration. And above all, integration with real turbopumps, which deliver high mass flow rates at high pressures, is the next big hurdle. The NASA TDM project is aimed precisely at this integration. With a methane-oxygen single-shaft turbopump and a combustion chamber in the 10,000-pound class. If this really works, then we're talking about the first real RDR-RDRE on the path to a flight-ready configuration. Right now, we're still in the demonstration phase. What remains is the strategic question. Who will win the race? If you honestly assess the situation in May 2026, the United States is in a position that seems unbeatable for a certain subsystem. NASA Marshall has reached the validation stage for civilian technology. Venus Aerospace has delivered the first flight. Astrobotic holds the endurance record. DARPA has the money and the military mission. Air Force Research Lab handles the long-term research. That's a 4 or 5 tiered value chain that doesn't exist with this density in any other country. Germany and Europe have something that the US doesn't necessarily have in one place. Namely, the scientific depth and methodological rigor that are necessary for a truly understood technology. What Europe lacks is an industrial policy path that translates this depth into an operational program. An ESA variant that would say, in the next 10 years, we will build a flight-capable RDR-RDRE for the upper stage of Ariane Next, or, for example, for a European reusable lunar landing system. There is no such roadmap, and as far as I know, it is not in preparation either. What does exist are excellent DLR publications, small test stand campaigns, and the first liquid oxygen test in Europe. And the quiet knowledge that DLR Lampoldshausen would be the next partner in any serious European program. But no program. China is taking probably the most controversial, but also the most strategically sober path. They are investing in RDRE technology primarily for hypersonic weapons development and secondarily for civilian applications. And the dividing line between the two is thinner there than in the US, and non-existent compared to Europe. What comes out of the Beijing Power Machinery Institute as a Mach 16 concept paper will show up as a hardware demonstrator somewhere in a facility within 2 years, and we probably won't be able to confirm the existence of that facility until long after the test. This is a game with different rules, and it will change the Western perception of technology once again. Japan is the quiet pioneer that made the first flights and plays the central validating role in scientific literature. Probably in a few years, when the first commercial use of RDRE is applied in a lunar lander or a hypersonic demonstrator, people will look back and realize that Kasahara's group in Nagoya in 2021 was actually the starting point. No one knows today who will win that. The likelihood that the first flight-capable operational configuration will come from the US is high, because money, vision, and validation are all there at the same time. The scientific depth is carried by Germany and Japan, and the fact that China is already further ahead in secret than public literature suggests is part of an honest risk assessment. But one thing is clear: the detonation, which for decades was the specter of every engine development, has finally gone from being a test error to a design principle. And whoever ignores this will still be building Vulcan Vinci architectures in 10 years while others are flying with annular combustion chambers. My name is Serwin, and this was Mars Chronicles. Thanks for tuning in. Per aspera ad astra. This video was created in collaboration with WalkMe. Mars Chronicles makes space systems understandable. WalkMe Learning Arc does the same for enterprise software, making complex tools easier to learn in the flow of work. Most employees forget 80 to 90% of what they learn in training within days, because traditional courses happen outside the flow of work. A new approach to enterprise learning is emerging: AI native training delivered directly inside the apps people use every day. Learning in the flow of work. It delivers micro-learning, courses, and learning journeys directly inside applications like SAP, Salesforce, and ServiceNow, triggered by user behavior and role. Built AI first, not retrofitted. It complements your existing LMS rather than replacing it, and for SAP Enable Now customers, it's the direct migration path. Learn more at walkme.com.